Hello everyone, welcome back. So we talked about different kind of flexures. We talked about their applications and what is their use. So in the last lecture we were talking about cross flexures. So we have two sheet flexures here, and if they are crossing, what we find is very good hinge. So we have the rotation axis, and we can just replace any kind of revolute joint with these kind of flexures. So we call it cross flexures. So wherever we have a axis, rotational axis requirement. Moving on, what what if those two sheet flexures, they don't cross each other, and so what if they are parallel? And what we realize that if they are parallel, so for instance here, if it's parallel, then what we can say that is the intersection is at the infinity. And so suppose if we try to get a rotational axis there, so actually we will get the translation at this point. So this is what we get. So we can just see it here. So I can move, and we can see the top part with respect to the bottom is just moving in a parallel plane, and that's why we call it flexural parallel guiding. And this is the topic for today's discussion and lecture. So when we have two sheet flexures parallel, what happens? So yes, parallel displacement in a plane, and if the stroke is very small, then we can approximate a straight guiding as well. So wherever we need a kind of straight guidance for a shorter stroke, we can always use these kind of flexures. And essentially what we are doing is we are using two sheet flexures in parallel configuration. So that's what we just observe. What we also realize that, so I just 3D printed, and by design what I have done is I created a gap here, but as we move, this gap gets closed. So but it's also acting as a safety mechanism. So it can be used as a mechanical stop. So very confidently I can simply push it without breaking it, because I know that after some displacement in x direction, there will be y direction displacement, and then it will touch the bottom part and it cannot move. So I don't have any kind of I don't have to worry. So you can see that I can just press it, and so very robust design we can get. Yes, we have to be aware of this, that there will be shortening effect. So as we move in the x direction, there will be y movement, in this case moving downwards. So there is a negative y direction couple, and it's a very small, and it's a function of minus 0.6 delta x square by L. So for a displacement x, this is the, so negative sign is downward. So there will be, so that's why it's called shortening effect. So it's a parasitic motion. It's not intended, but since it's related, if there is a x displacement, there will be related very small y displacement as well. So yes, we have to be aware of that, and we need to understand that if it's not desired, then maybe we have to find a way to eliminate that. And that's why we don't call it generally, yes, we call it a straight guidance, but yes, if we go by this definition, what we are calling it is parallel guiding, because it's getting guided in the, it's moving in the same plane. So if we are using this kind of flexures for our application, there are few things we have to look at. Of course, the stiffness is very important in the actuated direction. So if there is a force applied, any actuator is there, and if there is, we are getting any kind of displacement, how is it related with respect to the force? So of course the stiffness along that direction, in the driving direction, is very important, and many times we want to minimize that. It's a compliant direction, so we may want to minimize it. At the same time, we are also looking at the bending stresses developed. So because of that translation, the X translation, what is the associated bending stresses on the members? So these sheet flexures, so they are getting deformed in bending, and there will be bending stresses. So, and that's what limits the overall movement. Of course, the stiffnesses will also depend on that, and that we will check. At the same time, we are also looking at in plane guiding stiffness ky. So, what is the stiffness in this direction? Because that's what supports the load, any kind of payload we have, and if we are moving, that's what is supporting. So, we want to have a very high ky, but as it moves, we may find that this ky is a function of x. So, what are the limitations? So, I think these are the few parameters we will be interested in while designing this kind of flexures for our application. So, if we closely look at it, what we realize that the sheet flexure, there are two sheet flexures parallel to each other, and if we just consider one sheet flexure of the parallel guiding and the deformation what we have. So, we can just use the general formulation what we derived in the first lecture while covering the compliant mechanisms. So, what we observe that if there is a force F, actuator force, there will be delta x displacement. At the same time, there will be reaction moments and moments applied, and there will be associated deflection psi, because it's a guided. So, that's why we have to use the general formulation, and then we put the boundary conditions and we try to find what are the stiffnesses. So, we just follow the general equation, and we can write in terms of forces and displacements. And so, here what we can definitely write F, that is the force vector, and then we have the stiffness matrix what we have here, and it's related to delta x. Again, it's a vector which defines delta x and psi as well. So, yes, in the previous lecture, what I showed is the relationship between the forces and the displacement. We can just shuffle it and can rewrite, and we can write forces in terms of displacement, and that's how we can write the stiffness matrix. So, it's a general equation for any kind of cantilever, and when you have a forces acting at the tip, force and moment, and the associated displacement delta x and psi, this is how they are related. We can, if you are interested, you can always go back and check, and if you have any doubt, you can always ask, and we can again discuss. So, in case of parallel guiding, what we realize that the angular deformation is 0. And when we implement that, what we realize that, so F and X, they are related through this element 12 EI by LQ. So, if we write the stiffness in the driving direction or in the direction of F, this is what we get, and which will be 12 EI by LQ. Here also, I think with the one sheet flexure itself, what we can see that the stiffness value, if we check, the stiffness is the parameter of this I. Of course, E is the material property, but I is the cross section. What is the cross section and what are mm, the width and the breadth, and of course this is LQ. So larger is the stiffness will be lower, so we can get a very high compliance value. So the stiffnesses can be very low. So that's why it's very important to understand that L, the longer the length, smaller will be the stiffness, and to the power Q, so it will have a very large bearing. Uh, at the same time, I, if we take for rectangular cross section BDQ by 12, the thinner section we are talking about. So again, it's a to the power Q. So it will again have a large bearing. So so a smaller I means it can comply easily, and the stiffnesses value will be low. So just remember this K value is for one sheet flexure. When it comes to maximum bending stress, which will occur at the clamp. So at this point and this point, uh, it will have the similar values. So the maximum stresses will be at those points because the bending moment will be the maximum there. And we can always write sigma by y equal to m by I, and bending moment if we replace and we write in terms of h delta x and L square, this is what we get. So the stresses will be 3 times E h delta x, so function of delta x, and over L square. Again, larger the length, the smaller will be the stresses values, the maximum stresses. It means we can have a larger displacements. So we have to be aware of this, and this is what limits the stroke. So how far we can go, how far we can move. So this is the delta x, that's how much we can move. So it just tells you like, okay, how much x displacement in the driving direction we can have without failing. So sigma b maximum, what is the limit, and definitely we can have delta x. But of course, in terms of performance, there are other parameters. So we might be looking at the stiffnesses both in the driving direction and also in the support direction, for instance, in y direction, in plane stiffnesses. So what is the effect? I think we have to be aware of, and that will also limit this delta x. So when it comes to the flexure parallel guiding, now we have to remember there is one and two sheet flexures, and therefore when we are talking about this stiffness in this direction, kx total is in parallel, and therefore it will be 2 times the individual stiffness of the sheet flexure in that boundary conditions what we applied. And of course then it's a 12 EI by LQ, and total stiffness in the driving direction will be 24 EI by LQ. In terms of stresses, it will be same because the deformation is still same on each of them. So the sigma max will still depend on delta x, what is the displacement, and we can accordingly calculate the stroke length. We might be interested to know what is the force application point where we should apply the actuator or the actuation force, what is, and whether it has any bearing, any effect on the overall performance of the system, because we are interested in precision, and any kind of deviations we have, I think we should know, and we should find a way to eliminate that. So for instance, if we have this case and just we generalize and we apply this force F from point, suppose this is our reference, and from this, if this is the A, and this is my length of the flexure, what happens? So, when we try to write the force balance and free body diagram, if we make for this green object, the shuttle we call it, or the mass which is moving, which is suspended, or it's a kind of suspension design as well. So, assuming that these two flexures are identical, same thickness, weight, and the length. So, if we assume that, then what we realize that even these forces at the point at the connections, the forces will be equally shared. So, K1 equal to K2 equal to K, which is nothing but F by 2, because it's just shared is, so x direction what you have, so it will be opposed, so F by 2. Similar kind of deformations we have, so we can also assume m1 equal to m2 equal to m. What happens in order to balance, and if we try to see the forces in the vertical direction and in the moments, what we realize, there will be n1 and n2. The magnitude will be same, but the direction will be given by this, because the net force in y direction is n1 and n2 itself. So, they are equal and opposite, and they will balance the force, the moment, because of the applied force as well. So, if we suppose call a point A here, for instance, and just try to balance moment A equal to 0, what we realize that if we write the equation of motion and the moments acting at on the body and try to balance at A, what happens? There are two m, so m1 and m2 both working in the same direction. So, in this case clockwise. So, if you take clockwise as a positive, so 2m, and then Fa in the same direction, F times this displacement A. So, that will also give you a moment. So, that's added, and to counterbalance we have n times B. So, this is what we get. So, this is in terms of the forces N and M. But we also realize that if we take the individual leaf spring or the sheet flexure, so there will be phi and M acting and K, and we just use the bending equation, simple bending equation. What we realize that phi will be the function of KL square, the force, and the by EI minus the moment M L by EI, and that has to be 0, and that gives us M equal to KL by 2, where K is F by 2. From here we know that K is F by 2. So, if we put F L and 2 will come 2 to 4. So, F L by 4, and if we just use that formulation and put it here, what we realize that N times B is equal to F into A plus 2M, and 2M is nothing but 2 F L by 4, which is 2. And if we try to just rewrite, what we realize that if we write in terms of F and the geometric parameters, so if we can take it out, and inside in the bracket we will have A plus L by 2, and in the denominator we have B. So, this is what we have. So, what we also understand that apart from N1 and N2, all the forces acting on the individual sheet flexures are same. the geometry, everything is same. So we can say that it will have a similar deformation and there will be no angular displacement. Moment there is a non-zero value for n, if we check the loading conditions on the two sheet flexures, they are different. It means they are going to deform differently, and therefore we cannot have the same or psi equal to 0 because slowly it's going to tilt. So it's a very important to understand that even if we have the similar or identical sheet flexures used for this application and we have the parallel guidance mechanism, and unless n1 and n2 equal to 0, we cannot achieve a perfectly parallel guidance. So in order to have that, in order to have a size equal to 0, so no tilting, we have to also ensure that n should be 0, and for that what we realize that the numerator a plus L by 2 has to be 0, and therefore what we realize that this a value, the a what we have chosen, it should be minus L by 2. So it should be negative and half. So negative means this was the reference we have used. So it should be in the other direction, and L by 2. So halfway. So it should be halfway. So force applied should be halfway to the flexures. So we cannot just place the actuator anywhere, otherwise we will have some kind of tilting. So if we go by that and we want to have a 0 tilting, even though if we have a parallel guidance, it's very important that the the force, the point of application of force F should be halfway, and that's what is written here. The line of action for F goes through the middle of the flexures. This is the condition, and this is also called center of compliance because it's passing through the center of compliance, and that will be midway to the flexures, midway of the flexures, and it's called center of compliance because if you apply the force there, we'll only get the displacement in the F direction. There will be no other associated displacements. So this is what I was trying to emphasize, that if it's not there, then the loading conditions will be different here. So n will be different, n1 and n2 will be different, and because of that there will be angular displacement, and after some time you can see a tilting. So there will be a tilt, and therefore if we want to have a free of tilt suspension for this body L, this F should be applied at minus L by 2. So it should be at in the halfway. What are the other important aspect is not only that. So what we are doing is, or considering is, the quasi-static condition. So force is applied slowly, but for any dynamic application there will be inertia effects as well. So that's why it's saying, it said regardless of the frequency of force F. So if you want to eliminate that part, because if the CG is somewhere else, then the forces, the dynamic forces will be acting at that point, and if it's away from the middle part, it will also give rise to moment. So then what is required is even the center of gravity and center of compliance, everything should be here halfway. So center of gravity must coincide with the center of compliance. So for high speed application, for dynamic application, and also looking at the at a suspension design, parallel guidance system with the free of tilt behavior. Then it's very important that the actuator placement, the center of gravity, they should all lie to the center of compliance. And of course, we discuss about the stiffness. So 2 times the 12 EI by LQ, that's the stiffness in the driving direction. What we might be also interested to know is what is the effect on guiding stiffness if there is any displacement, any movement in the x direction. And so for instance, in this case, it's a supported here. So infinite rigidity, what we can see, what is the stiffness in the in plane direction, and this is delta x, it has deviated already. So it can happen because of the assembly errors. So when we are assembling, we know that the good thing about the compliance and the exact constraint design is it will absorb any kind of error we have, but definitely we'll have this error, zero error, and because of that the configuration may change. It may not be there where it should be, but there might be small displacements, and because of that there will be change in stiffnesses as well. Yes, here what we also see that there is the nomenclature, and in many of the books, in the Professor Suma's book, the stiffness is often written by CY C. So I'm using K because many of the Indian books and the books we refer, American books or by international authors, many times we use K for linear stiffness and kappa for rotational stiffness. So yes, here just be aware of that, and so I'm using the same formulations. So CY here, so it's for the stiffness in the y direction, so again linear stiffness, and this is how it's related. So if one is interested, we can always look at the references on the advanced materials, advanced solid mechanics books. But if we look at the plot, this is delta x by h. So h is the thickness of the sheet flexure and delta x is the displacement. So if we displace it, and of course it's normalized with respect to the thickness of the sheet flexure, and if we compare the stiffnesses Cy with respect to Cy naught when it's a means when it's a vertical or there is no displacement, x displacement. If we compare, of course, when at 0 it will be 1, but as we move away and if there is a displacement, what we realize there is a sharp decline. So if it's 10 times, delta x is 10 times the h displacement, is already reduced to maybe less than 0.4, right? It's reduced to that level. And if it's 5 times, this is roughly about 0.7 or 0.75 times. So this is what considered as the normal range. So yes, when we are designing, we should always take care of this. Although we can have a very large stroke because it's a very compliant, and the sigma value can be still low even though if we deflect too much. But at the same time, we lose this stiffness if we are moving too far from the neutral position. So it's very important to also understand that part. H, of course, suppose if it's if we are using sheet metals of 0.2 or 0.3 millimeter, and if you are talking about only up to 5, so H is for instance only 0.2 mm, then the the delta x max with respect to this, so that we have a reasonable value of Cy should limit or should be less than 5 times 0.2 mm, which is equal to 1 mm, right? So, it's a very important. There are a lot of boundary conditions. So, it's not just the failure, but there are other, the stiffness is there, the stiffness in the compliance direction, stiffness in the guiding, the bearing direction, load bearing direction is equally important. So, I think one should be aware of that while using this kind of flexures, and particularly when one is interested in knowing the precision, knowing the dynamics, because if it has deviated and then assembled, then if we do the model analysis and if we look at the frequency response, it will be very different from what is desired. So, I think one has to be aware of this and then try to mitigate these problems. But what happens if this stiffness, the support stiffness is not infinite? In the previous case, what we are saying is infinite, but what if it has a limited value? And what we realize that it's even worse. So, what we just covered, this is the black line what we have, and again we are comparing Cy by Cy naught with respect to delta x by h, and suppose if we limit to only this range, what we realize that the support stiffness has a lot of bearing as well. If it's infinite, we are here, and that's what we said earlier, that is of the order of maybe 0.75. Yeah? The reduction is of the order of 25%. But what if its CD value is not infinite, and so if it's just on the air, right, not supported at all, you can see that it drops even below, right? It's very small. If it's 10 times CD by Cx 10 times, and that's why it's very important to have a large ratio. So, suppose normally we say at least 1,000 times. So, if we are going for 1,000 times, we are very close to the black line. And so, these are kind of rule of thumbs, and uh, we talk about these numbers not just for the sake of saying it, but it has a lot of implication, design implication, and it will take care of a lot of things. So that's why it's important to understand why we are saying about or talking about those numbers. So for instance, CD by Cx, for instance, here we are saying 1,000, at least 1,000 times. So just be aware of that, and it will have a effect on the overall stiffness, support stiffness. But we also have to realize that this design is over constraint design, and this is very evident because we have three constraints from each one, but still we have one DOF, which is the displacement in the x direction. So what we realize that this phi 1 and phi 2, they are constrained twice. So of course then we lose one constraint, and because of that we get one DOF, which is the displacement in x direction. So if it's not perfectly parallel, then it will over constrain the system and difficult to get the same stiffness what is calculated or what we may like to have. And many times we want to get rid of that, so relief of over constraint in phi direction, and for that we can use additional rotational freedom in the flexure. So one we can do, so what we can do, we can create whole flexure, So we'll be talking about that in the coming lectures. But at the same time, we also reinforce it so reinforcement also we'll be talking about. But yes, this is one of the way. So we added rotational compliance, and then we have 3C here and 2C here, and so 5C and 1 DOF exactly constrain. Or what we can do is on the other side, this side, we put this cross, so torsionally compliant member, which again gives us one degree of freedom, rotational degree of freedom, or we can say it releases one constraint from this sheet flexure. So again, from this side we have 2 constraint, and here we have 3 constraint, and overall we get 5 constraint, and we'll just get the translation. So this is the basis. So if we talk about the principle and just use a wire flexure or articulated link, or what we can say even the constraint line approach, this is how we do in one plane. These are the 3 constraints, 1, 1, 2, 3. They will define one plane, and 4 and 5 again, they can define a plane with the whole flexure. So we can have a 2 parallel guidance, 2 sheet flexures, and we can achieve a parallel guidance system. So talking about the shortening effect, is a second order shortening, and we can compare if it's just articulated link, and this is the length and jet for a small displacement in the jet direction. This is the associated delta y, so we can write in terms of that. So we can always use the trigonometry and can find here, since it's a continuous member, it's a beam, so the deformation is there, so we can always have a equivalent. And what we realize, that's why I think this 0.5 becomes 0.6, and the z square by L. So just be aware of that. And sometimes we use the analogy and then try to find the hinge point, and we can also work with that. So just a derivation, so in terms of cos, and then when we approximate, this is what we get. So this is the shortening effect, and sometimes it may not be desired, and we just want to have a straight guidance, or we don't want any kind of movement from the axis. So suppose this is the gray is the fixed frame, and this is the orange part is the body which we want to move in a straight line. So how to compensate for that thing? So what you can see that we have used like number 1 and 2 sheet flexures. In plane it can be a wire flexure, or yeah, but so in 2D if we see, it looks like this. So in depth wise it can be sheet flexures, we can assume. So 1 and 2, if we see from orange to the this green body or cyan body, what we say, we call it intermediate body, there will be movement delta y. So it's moving along this side. But if we connect it back to the frame, so that will get compensated. And therefore, what we realize that the orange body will have only vertical motion or straight line motion, because it's getting compensated. So from from gray to green, what you can see, there is a movement inwards, and again that's further compensated. So from green to orange body, it will again pulled back to delta y, and then the net delta y movement for the orange body with respect to gray will be 0, but there will be x displacement, but we also realize that x and x, the displacement in the vertical direction for the intermediate body will be just half of the total displacement we have. So there is a half displacement also. So we'll stop here, and we'll be talking about reinforcement and how it improves the performance of any kind of flexures, and we'll take up some examples, and then again we try to see what is the effect on the load bearing capacity, how it affects the stiffnesses, and also the stiffness in the bearing direction, or what we can call in plane stiffness. We'll stop here today, and then we'll continue with the next section in the next lecture. Thank you.